Hello, my name is Bernd Brach, and I will present the paper Almost-Orthogonal Layers for efficient, general-purpose Lipschitz networks, written together with my advisor, Christoph Lampert. Deep networks are often the undisputed state of the art when it comes to solving computer vision tasks with high accuracy. However, the resulting systems tend to be not very robust, for example, against small changes in the input data. This can make those models untrustworthy for high-stakes tasks, such as autonomous driving. A typical example of this phenomenon are adversarial examples. Imperceptible small changes in input image can drastically change the output of a deep learning classifier when chosen in an adversarial way. Researchers have developed plaintiff defenses against adversarial examples. However, new attacks usually break those defenses. Therefore, we want a more principled alternative that guarantees that networks are robust against any attack. One way of achieving this is by using layers that have a small Lipschitz constant. We call a layer or function one Lipschitz if for any two inputs, the difference of the corresponding outputs is most as big as the difference of the inputs. Other researchers have proposed various different layers with bounded Lipschitz constant. They usually rely on either orthogonally or an upper bound of the spectral norm of the weight matrices. However, those layers are often very restricted, for example, to fully connected layers or convolutions with a very large receptive field. We combine both ideas and use orthogonality with an upper bound in order to create a method that has advantages from both. In order to create one Lipschitz layer, we construct an upper bound of the spectral norm of a rescaled matrix. For any parameter matrix B, we define a diagonal matrix D by the term shown. Then we prove that the spectral norm of the product of the matrix product of P and D is bounded above by 1. We use this to create a fully connected one Lipschitz layer by rescaling the parameter matrix of the layer as defined earlier. Note that when the parameter matrix P is already orthogonal, then the matrix D is the identity matrix, so no rescaling takes place. The proof of the theorem consists of finding an upper bound to the elements of P transpose P and can be found in the paper. Since most well-performing networks require layers with more structure than dense layers, we also propose a way of rescaling that works efficiently for convolutions. In order to do that, we find a rescaling for each input channel that ensures the convolution is one Lipschitz. The computation of the rescaling factors uses a self-convolution of the kernel and therefore does not depend on the size of the input. Therefore, we can use this convolution efficiently even for very high resolution inputs. We call a method AOL for almost orthogonal Lipschitz. We create networks using those AOL layers and compare them to related work by measuring the certified robust accuracy on CIFAR 10 and CIFAR 100. We reach competitive results. In particular, for our hyperparameter setting, we do perform well for higher maximal allowed perturbations, the measure which we deem more important. We also present some ablation studies in the paper, showing that our method generates approximately orthogonal weight matrices, justifying its name. We also show that we can trade off standard accuracy and certified robust accuracy by choosing the hyperparameters of a loss function, and that we can use our layers in a range of different architectures and get competitive results. Summarizing, we propose a technique that we call AOL for almost orthogonal Lipschitz. It makes fully connected as well as convolutional layers guaranteed one Lipschitz. We use it to construct networks that reach competitive certified robust accuracy. For details, check out our paper, Almost-Orthogonal Layers for efficient general-purpose Lipschitz networks.